Raw data, a long list of values, are hard to make sense of. That is the reason we often use summary statistics to describe raw data. Summaries simplify. In fact, summaries sometimes can oversimplify, which means it is important to know when to use summaries and which summaries to use. Often the right choice depends on the shape of your distribution. To help you build your visual intuition about how shapes and summaries are related, this first video introduces various shapes and asks you to estimate some summary values visually. Later videos will tell you how to compute summary values numerically. Distributions come in a variety of shapes. Four of the most common shapes are illustrated in the rest of this video. The shape we'll look at is the uniform or regular distribution. We'll call it uniform in this class. Uniform distributions are rectangular in shape. This is an example of data that has a uniform distribution. Notice that we're dealing with the number of people born in thousands each month, starting in January all the way to December. Notice that about the number of people that are born are almost equal. Yes, some of the heights are slightly different, but those are close enough that we call this uniform. The overall shape is a rectangular shape. The plot shows that there is actually little change from month to month. That is, we see a roughly uniform distribution of the number of people born across the months. To summarize this distribution, you might write, the distribution of the people born is roughly uniform over the months January through December, with about 340,000 births per month. Include the two key data, the range January to December and the approximate frequency, 340,000 births per month. The second type of distribution you need to know is symmetric distribution. And a specific example of a very common symmetric distribution is called the normal distribution. A symmetric distribution is a type of distribution where the left side of the distribution mirrors the right side. By definition, a symmetric distribution is never a skewed distribution. We'll talk about skewed in a moment. The normal distribution, pictured here, is a special type of symmetric distribution. The best way to describe the center of the data is through the mean, which is the 0 point labeled here, the middle of the U. If you go one standard deviation from the mean in each direction, you will hit the inflection point on your normal curve. This inflection point is where the graph changes from concave up to concave down. Now, standard deviation is just simply a measure of how spread out the numbers are. We'll look at calculating that in one of the following videos. But this highlighted area in between, that represents 68% of all the data if your distribution is a normal distribution. We're going to learn more other important information about the distribution of data in the normal curve in coming chapters. The best summary statistics for symmetric distribution is the mean and the standard deviation. Mean from the measure of center, the standard deviation from the measure of spread. So let's look at this. This is pretty symmetric. We have a mean about here in our data, and we have the exact same shape, curvature on each side of that mean value. So I'd say this is pretty symmetric. So let's say the mean is about 510. We got that nice symmetric curve going on each side. So I'd say a standard deviation is about when I switch my inflection to concave up to concave down, and then concave down to concave up. And I'd say that distance is about 90. Again, all I'm having you do right now is to estimate based on the picture. We'll learn how to find these exact values later. I got a sentence summarizing this picture distribution using our summary statistics. So I'd say something like the distribution of SAT 1 math score is symmetric and has no obvious gaps or clusters. The distribution is centered at approximately a score of 510 with a standard deviation of approximately 90. Our third basic distribution shape is called skewed distribution. Here we have a picture of a distribution that's skewed to the left and skewed to the right. Let's look at this skewed to the left distribution graph. Notice that majority of my data is on the right, and then I have it tapering off on the left-hand side. This part is called the tail. So if the tail is pointing to the left, we would say this is skewed left. If a skewed right distribution, the tail is pointing to the right-hand side, and the majority of our data is on the left. So this is skewed right. Sometimes skewed left will be referred to as negatively skewed, because our left is on the negative side if you're thinking about your number line. And a right skewed will sometimes be referred to as positively skewed distribution. Again, because on a number line, the positive direction is to the right. So let's look at this dot plot. Here we have some data, and it appears that this data is tailoring off to our left, so we would say this is skewed left. And this data represents the grade point averages of 62 statistics students. When we look at skewed data, because of the tail pushing out some information, our mean will go closer to the tail. So if I have a right skewed distribution, our mean is closer to the tail than our median. Because the tail pushes that mean away from the center of our data, the best summary statistic for skewed data set is the median. And the best measure of spread would be our quartiles, which we'll use to calculate our interquartile range. Median is the middle number when your data is in increasing order. The lower quartile, called Q1, is the median of the lower half of your data, separated by the median, and the upper quartile is the median of the upper half of your data. Looking at this distribution, notice that we have a kind of skewed distribution. We have majority of my data on the right-hand side and the tail going off to the left-hand side. So I'd say the weight of bears in pounds is skewed to the right, so skewed right. Now I've taken the same graph and I marked about where our lower quartile, our median, and our upper quartile would be placed. If I actually counted up all these points and figured out the number in the middle, and then looked at just those lower values and found the number in the middle, you get lower quartile, and look at the upper values, find the number in the middle, and get the upper quartile. Let's find a sentence to describe this distribution. The distribution of weight of bears in pounds is skewed right. The middle 50% of the bears is weighted between, and we want to figure out the value of our lower quartile and upper quartile. So 50% of our bears is weighted between about 115 and 215 pounds, with half above our median, which would be about 155 pounds, and half below. Let's review this a little bit. If you have symmetric data, your mean and your median are located in the middle of the data and they're about equal to each other. So mean is approximately equal to the median in symmetric. But we will use the mean to describe our data because it's a little bit more exact in most cases. So this is our best measure, a center for symmetric. If our data is skewed left or skewed right, we're looking at skewed left, our mean will be pulled toward the tail of the graph. So our median will be closer to the more center of our main body of our data, and our mean will be moved toward the tail. So we would say our median is the best measure of center for this data. Right skewed, on the other hand, the mean is pulled toward the tail, so it's moved to the right of the median, and our median is more here toward the center of our main part of our data set. So again, with right skewed, we'll use our median as our best set. The last major distribution that we will see is bimodal distribution. A bimodal distribution has two peaks in our data. Here's an example of life expectancy of females by country on two different continents. Notice how our distribution has two main humps. So we would say this is bimodal distribution. So we could say distributions can be unimodal with one peak, bimodal with two peaks. And when they have more than two peaks, we kind of lump them together and say multimodal. Distribution is bimodal. Reporting a single center isn't enough information because we have two main areas in which our data is centered. And our single center would be in between these two humps. That could be misleading. This is where our measure of center would be if we did not take account that we have two main peaks. And that could be misleading to a reader and not very useful. So one reasonable summary is to locate the two peaks. However, it is even more useful if you can find another variable that divides your set of cases into two groups that center at the two peaks. So if we can divide these up to two graphs that are each unimodal, we could even learn more about our information. So I go back to my graphs here, and we're talking about life expectancy of females in 2 different continents. So why don't we divide these up by our 2 continents? I'm going to make one continent. Our first continent is Africa, and our second continent is Europe. So when I plot this data based on the 2 continents, if I just do the African data, I have a skewed data set, and this is skewed to the right. And if I plot the European data, I have a pretty symmetrical data set that has a mean about where our second peak of the bimodal data was at. By breaking it up into with the variable of continent, I was able to tell more about my information. So sometimes you have other variables or other things that you might need to look into to help explain your data set better. But not least, when you're describing a distribution, you would want to talk about some unusual features of a distribution. Some examples would be outliers. That's a variable that stands apart from the bulk of the data. Now, you might be an outlier because it was a mistake that you made in either measurement or writing it down, or it might be an atypical measurement for some other reason. Sometimes having outliers are a key to another important discovery. So let's look at an example of this third case. In the late 1800s, Baron Rayleigh was studying the density of nitrogen using samples from air outside his laboratory and samples produced from a chemical procedure in his lab. He saw a pattern in the results that you can observe in the data plot above. Lord Rayleigh saw 2 clusters separated by a gap. When he checked the clusters, it turned out that the 10 values to the left had all come from chemically produced samples, and the 9 to the right had all come from atmospheric samples. What did this great scientist conclude? That the air samples on the right might be denser because of something in them besides nitrogen. This led him to discover inert gases in the atmosphere. Just one example of the power behind good statistical analysis.